Welcome to iqpod.io, where Ava and David, your expert AI hosts, bring you the latest developments in the neural rendering and 3D reconstruction field. They delve into significant papers, offering detailed analyses and engaging in thought-provoking discussions about their implications.
Today's paper, DUSt3R, Dense Unconstrained Stereo 3D Reconstruction, is quite the tour de force in 3D computer vision. The core problem it tackles is how to reconstruct a 3D scene from a set of 2D images without any information on camera parameters, such as lens settings or the angles at which the photos were taken.
That's a challenge that's been historically difficult, right? Without knowing where the camera was or its intrinsic settings, constructing the spatial relationships within a scene becomes a guessing game.
Precisely. And this uncertainty has been a significant bottleneck for applications in areas ranging from virtual reality to architectural modeling. But this paper claims to have found a way around these limitations.
So, how does the paper set up the problem, and what's the method they've come up with?
Well, traditionally the process of multi-view stereo reconstruction, inferring 3D space from multiple 2D images, relies heavily on knowing camera orientations and positions. This reliance often leads to inaccuracies, particularly when there's a lack of data, like gaps in the image sequence.
Right. Those gaps in the sequence tend to result in incomplete or sometimes erroneous reconstructions.
Exactly. Now, the innovation here is that DUSt3R doesn't require predefined camera parameters. Instead, it uses point maps, which are essentially a dense grid of 3D points related to pixel positions, to directly regress the 3D structure from image pairs.
I imagine that makes the method quite versatile. It doesn't matter how the images were taken, just that the content is there to work with.
That's the beauty of it. DUSt3R processes the images using standard transformer encoders and decoders, components widely used in deep learning. These neural networks have been pre-trained on large datasets to understand geometric intricacies, allowing for accurate reconstructions even when camera details are unknown.
Interesting. So it's essentially distilling the essential elements from these 2D images and using learned patterns to recreate the 3D scene. That's quite a departure from methods like NeRF, neural radiance fields, and even Gaussian splatting, isn't it?
Right on point. NeRF, for instance, requires extensive computation because it operates on the principle of ray tracing, making it computationally expensive and sometimes impractical for larger scenes or those with viewpoint variations.
And Gaussian splatting, while faster due to its simpler rendering method of using Gaussians as a standpoint representation, does not provide as detailed a 3D representation as one would like, if I understand correctly.
Correct. Now, while Gaussian splatting is efficient, it doesn't capture the granular details that deep learning approaches like DUSt3R can. What's novel here is that DUSt3R's architecture, which harnesses the power of transformers, advances the field by delivering a method that's not only accurate but also considerably simplifies the pipeline for 3D reconstruction.
When talking about the results, they mentioned that higher image resolutions naturally lead to better reconstructions. But it does make me wonder, what resolution were the other methods operating at?
The paper doesn't explicitly state the resolutions used by the other methods in their comparisons, but typically high resolutions provide more raw data for the neural network to work with, leading to finer details in the reconstruction.
And the paper's results were verified against other state-of-the-art methods in real-world scenarios.
Yes, and that's crucial. For example, they could successfully reconstruct a 3D scene from two almost diametrically opposed images, which is quite challenging due to the minimal overlap. This kind of adaptability shows DUSt3R's potential impact. It simplifies the process and circumvents issues that have historically plagued 3D reconstruction tasks.
And does this improvement sustain when dealing with a larger set of images? Would more data points make the reconstruction even more precise?
Generally, you would expect that more images provide more data, leading to a more accurate reconstruction. However, with DUSt3R, even a minimal number of images can yield impressive results due to the neural network's predictive capabilities.
Let's delve into the intricate details of DUSt's method. The paper talks about the architecture used for 3D reconstruction. Ava, could you unpack that for us?
Of course, David. DUSt3R employs a network with transformer encoders and decoders, inspired by the CROCO method, which stands for cross-view completion. The network takes two RGB images as input and outputs point maps along with confidence scores. The beauty of this method lies in the implicit encoding of the scene's 3D geometry, sidestepping the need for explicit camera parameters.
Point maps, as in a direct correlation between 2D pixels and their 3D points in space.
Precisely. This correlation forms the bedrock of DUSt3R's reconstruction capability. It allows for the recovery of depth maps as well as the estimation of relative poses between images, contributing to the overall 3D scene structure.
So it's not just generating static point clouds, but dynamic, geometry-rich maps reflective of the original scene.
Indeed. And to validate their method, the authors set up experiments on standard benchmarks like DTU, Tanks and Temples, and ETH3D.
Those are based on challenges in MVS, right?
Exactly. They chose these because each presents its own challenges. DTU for laboratory conditions, Tanks and Temples for more complex real-world data, and ETH3D for diverse capture scenarios.
Which brings us to the results. What conclusions can we draw from there?
The conclusions are quite compelling. DUSt3R can handle varied reconstruction scenarios and even perform without camera parameters known prior, something traditional methods struggle with. The reconstructions were shown to be consistent and accurate, evidenced by superior performance in those multi-view datasets.
Did they discuss an ablation study to test the importance of different components?
They did. The authors showcased that the CROCO pre-training and the input resolution are crucial for performance. Pre-training on CROCO primes the neural network with a strong understanding of geometric relationships, which translates to better initializations for DUSt3R, and higher resolutions naturally yield more data for the network to analyze, enhancing the final reconstruction.
And what about the appendices? They often contain nuggets of extra insight.
The appendices provide additional qualitative results. Visualizations of the method working on real-life scenes with significant viewpoint changes. They drive home the network's robustness in practical applications.
Very comprehensive. And now to wrap up, what impressed you the most about DUSt3R?
For me, it has to be the point map methodology. It's not just an incremental step, it's a transformative approach to 3D reconstruction. By reframing the problem as a regression task and learning spatial correspondence between 2D and 3D points directly, DUSt3R circumvents the need for extensive pre-computation, a genuine leap.
I would say it's the versatility for me. The fact that DUSt3R can pivot from monocular to binocular reconstruction scenarios with ease is fascinating. The agility with which it infers and renders 3D scenes without needing time-intensive camera parameter estimations could have serious implications for real-time applications.
Absolutely. The paper stakes a strong claim in the field, setting a new bar for 3D vision tasks.
And with that, our deep dive into DUSt3R, dense, unconstrained stereo 3D reconstruction comes to a close, a paper that undeniably broadens the horizons for 3D computer vision. Before we sign off, a shout out to the authors of this impressive paper, Xuxie Wang, Vincent Leroy, Johan Cabon, and their colleagues from Aalto University and Naver Labs Europe.
Remember, this episode was generated by a large language model AI, and while we strive for accuracy, some information might be incorrect.